an astrophysicist. My background's in chemistry, but I dabble, I study, but it's not just make-believe.
Now, here's another question, is on this Hawking's process, it says that black hole sooner or later will evaporate, right?
Right.
So, is this because the two black holes that are
No, that's a single black hole in and of itself, and it has to do with what the black hole is made of this strange sort of particles. And if you watch a video on the Hawking process where black holes evaporate, it has to do with particles and antiparticles kind of annihilating themselves. And it's only the small black holes evaporate more quickly than the large black holes. It's kind of like if you
two black holes that are going round and round in the big black hole. Would that help
that would take a while. No.
Would that help the process of
evaporation? No, the
okay.
Hawking process of a black hole evaporating. No, that's kind of no. But I brought these actually in. I don't have videos on Einstein, but what I did is we talked about, it's called length contraction, and the faster you're going relative to somebody who's not moving, your length will get smaller and smaller. And then if something's traveling the speed of light, the length goes to 0. We had the Girl Scouts out at the observatory last night, which was a lot of fun. And actually, I kind of talked a little bit. I can't remember the context. And she said, well, it would go to 0. I'm like, you're right. Oh, my gosh. I don't know. It gets exciting when they get it. So another thing, and again, his equations are solid. So his equations then say that if you're traveling close to the speed of light, then actually a clock, or time, not a clock, literally time, will unfold more slowly. Not in your frame of reference according to you, but in somebody in a frame of reference that's not moving. So remember how that works. Okay, so that's the whole twin experiment. And then the last one we said that, and I kind of giggle because those stewardesses, although they may age more slowly, they're more massive. So traveling the speed of light, you get more massive. Okay. So up to, and again, if you take that kind of into its extreme, at the speed of light, you have an infinite mass. It's bizarre. And then the last thing actually goes to his general theory of relativity. So do you guys remember, what does this over here, what happens, the clocks, and again, it's time, it's not the clock's malfunctioning, but how does time on Earth versus time on the moon do? 5 minutes difference, and which is more slowly? Which one? The Earth is more slowly. Yep, you got it. So those are kind of the outcomes. So instead of a video, I just kind of went that way. So let's take a look at that last part. And at the crux of this last part is something we've talked about. If I were to, and I don't have this as a test question, if I were to ask you a yes/no question, do most stars have a companion? You say yes. Does our star have a companion? There's been some, Star Trek had, was it the Nemesis, right? So, there's been some talk about our sun, does it have, or did it used to have a companion star? I don't know. Maybe there's still a little bit of discussion about that. But as far as we're concerned right now, they're not orbiting a common center of mass like binary stars do.
I was thinking yesterday, could the asteroid belt been
another planet?
The companion star for the sun in it.
No, asteroid belt. Actually, I think we talked about it. If you were to take all the little crumblies, it wouldn't even be as big as a planet.
Oh.
Even though it looks like there's a lot, let alone another star. So, the biggest thing we have to maybe our companion star would have been Jupiter. If Jupiter would have gotten a little bit more bigger, actually quite a bit bigger, was it like? Thank you, 75 times bigger. That's closer than the asteroid belt. But if you have your, because we got time, do I have mine? Oh, I don't think I do. If you have your little maps, your sky maps, go ahead and take that out. Now the star Algol, what constellation is the star Algol in? Actually, it's on slide 2. It is in Perseus. Somebody said Perseus. So this isn't about Perseus, but what constellation is the W, circular C? Cassiopeia, yep. So find Cassiopeia on your star maps. Look for the W. Oops, Ooh, the union label. Look for the W. And then under the W, do you see Perseus? Yeah. Okay, yep. And then within Perseus, do you see the star called Algol? Great. And that's what this slide is about. So Algol used to look like this. Okay? Algol is actually, if you see, is it on the front or flip it over? Or maybe it's on the slide. It's an eclipsing binary. So what's an eclipsing binary mean?
One passes in front of
Yep. One's going to pass in front of the other, and then from our standpoint, the light's going to go down. Yep. So it's an eclipsing binary. And notice that we have, these are both main sequence stars. So which is the lighter of the two main sequence, as in less massive, the left or the right?
You say less massive?
Less massive. I'm liking the right. Why? Well, because it's smaller, but what color is it?
Red.
It's red, yep. So, yeah, so it's red. It's down here, and we have that one right here. So which one's going to age more quickly? The left or the right? The left one, yep. So next on the track for that star is, what would we call this phase? The left main sequence, what's this? Giant, super giant, yep, it's swollen. And what's it doing to its companion? Exactly, its companion is siphoning off material, exactly. So this definitely happens. It's a player. And if you read this, what the quandary is if we kind of follow this red one, it's the main sequence. You told me it's lower mass, it looks smaller, but it's lower mass. And it got stuff from its companion, and now actually it kind of morphed into something that generally it probably shouldn't morph into. Okay, now it's picked up some energy, and it's brighter, okay, and whiter. So with that in mind, let's kind of talk about what can happen in binary star systems where one star is swollen and can dump on its companion. The companion can siphon off material onto itself. So these are all different things. So the first scenario is a white dwarf. Okay, white dwarf in a close binary system with an evolving low mass star. The evolving low mass star just means it's swollen. Okay, so this is swollen, red giant. We have a retired star right here. Now, I talked about this the other day. Kind of this stuff starts with letter A. It starts with letter A, and then the second word is disk. What do we call this?
Accretion.
An accretion disk. Perfect. Yep. So it forms an accretion disk. Okay. So I think that's about all I'm going to say. And kind of back to the signatures we were talking about, the different wavelength signatures. We can probably see this, if this is a white dwarf, probably just kind of heating up, maybe in infrared, kind of a warm sort of accretion disk. Okay. So I want to talk you through something I thought I talked you through it before, but I got my semesters mixed up. I want to talk about what's called a nova, not a nova, but nova event. So nova events look like this, where this little blue thing right here, that's your white dwarf, and here's its companion, kind of lagging behind, right? Because this one's already went through the bloated red giant stage. Now it's retired, and this guy is going to be able to dump on it. So in the nova event, what happens is, and I call it kind of a blanket of material, and here's a picture of it happening. It's kind of the white dwarf is retired. What's at the core of a white dwarf? Do you remember what element? Starts with letter C.
Carbon.
Carbon and oxygen, probably. Yep, carbon and oxygen's at the core. Yep. So it's done fusing. So what can happen is it gets fresh material here, and its core is carbon, but it's got like fresh hydrogen on the outside. So basically it gets more hydrogen from its buddy, because this would be hydrogen, right? This hydrogen adds to this hydrogen, and it creates the pressure and the temperatures needed for nuclear fusion to happen. This is different than what we call shell fusion. This is just this is surface fusion. So it's I like it like a blanket. It's kind of like a little mini explosion that happens when that nuclear fusion happens. It's like taking your blanket, it's like, oh, it's hot in here. Okay, and a little explosion happens. Now, the core of the white dwarf remains intact, okay? and it's got probably helium outside and then hydrogen there. The thing about this is nova events can reoccur. Okay, so then after it throws off the blanket, guess what? It gets more stuff. It can heat up to begin fusion and throw itself off. So that's nova events. Wish I brought my stuff, because on that sheet I gave you the other day, and we're going to talk one more thing about the initials are SN. What happens to a star that's more massive than 8 solar masses as it ends its life?
Supernova.
Supernova. Yeah. So this is nova. That's a supernova, right? You see, they're different, though, right? Well, there's one more thing that can happen, and this is the same scenario. This is the same scenario. We have a retired white dwarf, and we have it getting dumped on by a red giant. So Chandrasekhar came up with this limit that a white dwarf can be, and 1.4 solar masses is the most massive a white dwarf can be. And what happens beyond that is it kind of tries to, think of it this way, it kind of tries to squeeze its matter and make, what do neutron stars do? Take protons and electrons and turn them into neutrons. It's kind of what it likes to do beyond the 1.4 solar masses. So what happens here is, again, it gets its material, okay, but instead of being like a blanket that it just throws off with a nova event, it kind of adds beyond that. Okay, it basically keeps building and building in excess of 1.4 solar masses. And at that point, it has gone beyond just the whole, I'm going to throw off my blanket. It's gone to the point of, in its core, that carbon actually squeezes together, and I kind of think it tries to do the whole neutron star thing. And it begins to fuse, I guess maybe that's more likely. It begins to fuse, and instead of just throwing off a blanket, it blows up. Core and all, which would be the retired white dwarf star, it blows up. Now, don't blame me. There's a lot of things in science that I wish they had different terms for, and this is one of them. Do you see what they call it? It makes me so mad. You're like, can't you come up with another name? Because most people, when you say, oh, that star went supernova, you're like, oh, it was a massive star that ended its life. Most people think that way. But they also call this a supernova event. So you get my sense of grr if you're there. What they do is they go ahead and they add, it's a type 1A supernova event. Yeah. Okay? So we have 3 terms now that kind of, the supernova we talked about before, the nova, which can reoccur, the throwing out the blanket, and then the supernova type 1A where the white dwarf blows up. Isn't that kind of sad, like after you retire to totally just blow up like that? Instead of living your life to just kind of, so that's it. That's it. So I have some slides to kind of reinforce or talk a little bit about that. Now, I think when I've gone to this idea of whenever you hear me talk about a supernova, I'm talking about the massive star ending its life. But other astronomers will, instead of saying just supernova, they'll go ahead and say supernova type 2, Roman numeral 2. So supernova type 2, that's the same thing as course. Now, supernova type 1A was the one we just covered just now in class. And the white dwarf got beyond 1.4 solar masses from a companion star and blew up. These are, and I think we looked at kind of these decay light curves. This is just like along the y-axis here we have brightness. So it's showing you that, let's see, the blue one, massive star supernova. So this would be the type 2. This is the normal supernova. It looks like this blue one, where over time it gets dimmer and dimmer. What a rush to see those things though. Anyway. And then the red one is a slightly different decay curve for the white dwarf one, the type 1A. Now on the test, I'm not going to ask you to differentiate between these two. But if you know what you're looking for, you can kind of tell how the light kind of diminishes which one you're talking about. So there's that. So white dwarf supernova, AKA type 1A, right? The other thing is, how do we kind of differentiate between a nova and a type 1A supernova? They both deal with white dwarfs and getting matter from their companion star. Well, the supernova